Hello, and welcome back to Simulating Neurobiological Systems, Systems 556 and 750, taught at the University of Waterloo in the winter term of 2021. The topic for today is learning. And what do we mean by learning? So there's a general sense of learning, if you want to try to define what that means. Some people would define it in a very, very general sense, which is just, hey, if I have a system and I do something to it at one point, and then I do the same thing later on, and it behaves differently the second time, then it's learned. Doing some sort of, changing its behavior based on past experience, something like that. So that seems like initially a vaguely okay definition of learning. It's not quite what we're going to use here. And the problem is that sort of more general definition of, is the output different? If I do the same thing to it now that I did yesterday, but now it behaves differently, and so therefore it's learned. The problem with that definition is, well, the networks like the integrator that we already saw are already doing that, right? The network like the integrator, if its output is supposed to be the integral of its input, and so the output that it's doing right now includes all the information that's had in the past. So it's, the output that it does right now is going to be different than what it did yesterday, because it's adding up everything from its past. So that's not quite what we mean. Similarly, tasks like the symbolic tasks that we looked at a few classes ago, where we were sort of showing a sequence of symbols, and then it had to figure out, okay, what comes next. You could also sort of think of that, oh, well, clearly it's learning that, and it's learning that by seeing a bunch of examples and then seeing what comes next. Neither of those are going to be what we're going to be talking about here in terms of learning. What we're going to be talking about in terms of learning here is very specifically, I'm going to change the connection weights while the model is running. Okay. So we're making a big distinction between sort of all of the networks that we've seen so far in this class. We go through this initial phase of computing what the right connection weights are, based on us taking these functions, breaking them down into decoders and encoders, building up our big network, and then we run our network. But so far, everything we've shown, when we run the network, while it's running, we never change the connection weights. Okay. So that's what we're going to challenge right now. Okay, we are going to work on ways of, okay, once we start our model running, we're going to change the connection weights. Why would we want to do that? Well, there's a whole bunch of possible reasons. Let me actually pull up the course notes again, because there was a good section on that in here. So there's a variety of different reasons why we might. So ideally, we know everything we want our network to do. We just go ahead and compute everything. We have our connection weights done. We don't have to worry about this learning thing. Okay. But we might be in a situation, so for example, we might not know what the function is that we want to compute at the beginning of the task. So it might be that we're, the sort of task that we're interested in changes, so we don't know. So I don't know, it could be that we're wanting to have a system that will evaluate, hey, here's an object, should I eat it or not? But I just want to set up a general system that I could just give it some foods, and it goes, oh, okay, well, I eat this, and oh, I feel sick, so no, in the future I'm not going to eat that anymore. Okay. If we knew what exactly the function was, if we knew its environment was that it was interacting with, then we could figure out what the ideal thing is. Probably not going to be possible most of the time. Okay. So if we want something that will sort of be flexible to work in different environments, we might need some sort of learning, because we might not know what function it's supposed to compute. Similarly, the environment might change over time. So the desired function that we might want to do could, maybe I'm trying to control a robot arm, and that robot arm wears down over time, and it becomes, so initially, the command I need to send to the arm, and how much power I need to send to the arm to move it to a particular position, is one value, but later on I now have to send more power to it because the arm is not working very well. So I might need my system to, the function that we're computing might need to change over time. There's also the issue that when we say we're solving for the optimal weights, we are solving for the optimal weights under a couple assumptions. So one of those assumptions is that we're solving the optimal decoders, but those optimal decoders are dependent on our encoders. So it might be that there's a better set of encoders for this particular task. Okay. Also, when we solve for our decoders, we are assuming Gaussian noise. We might want to, that's not necessarily exactly right. We might want to be able to adjust that and deal with things, and sort of, there might be better weights than the ones that we solve for because those assumptions might not be completely valid. Okay. So those are sort of more technical reasons why we might want to have learning. We might want to say, okay, here's some connection weights. We can go solve for them initially, but then maybe we want to adjust them over time. But there's also a scientific reason, and that is, well, if my scientific interest is, okay, how do brains learn? Like so far in the course, we've been very focused on how do brains compute. But how do brains, so fine, if I have neurons, they're connected, they have particular connection weights between them, I can get neurons to go do lots of different tasks that we've shown so far in the course. But there's also this other question that a lot of people who are interested in neural networks are interested in is, well, look, somehow brains need to get those connection weights from somewhere. Somehow brains need to learn. Right? We're not born with the correct connection weights. There's not enough room in the genome to exactly specify those connection weights. Where do they come from? Okay. So if we want to do sort of the scientific inquiry into how do brains get those good connection weights, then we also need to build models of that process. Okay. Of course, when we start doing models of that process, now we got to be really picky about sort of, well, are we coming up with learning algorithms that could be implemented in brains and things like that? So if we're interested in learning about the biological process of learning, then we might want to be bringing in some constraints about what sort of weight solving, or so what sort of methods we can use to get weights. For example, it is very unlikely that brains are generating A matrices and inverting them in order to solve for decoders. That's very unlikely that brains are doing that. What else could brains be doing in order to get these weights? Okay. So all of these things seem to indicate that in addition to just sort of saying, okay, how can brains compute, it is also interesting to bring in these questions of how do brains learn to compute. Okay. That's what we're going to be talking about today. Now, one nice thing that we can do is look, there are tons of researchers out there who are looking at neural networks and how the neural networks learn. In fact, arguably, the vast majority of neural network research is in that sort of domain, and it's kind of odd to be doing what we're doing in this course and saying, well, hey, look, let's separate these two questions. There's one question of just how do brains compute. Just don't worry about the learning, just say what's the best job they can possibly do. And now we're going to bring in learning. A lot of people are just used to the AI just because they don't have the neural engineering framework as a structure. They sort of fall back in the thing of, well, there's just no way to do anything if you don't have learning involved. And that's sort of, I would argue, kind of a fairly dominant view in neural networks. But the nice thing is, because everyone's focused so much on what are sorts of learning algorithms you do in neural networks, one thing I could just do in this lecture is just simply say, hey, look, there's tons of research out there about learning in neural networks. When you do stuff with the neural engineering framework, all you're doing is you're generating a neural network. So once you've got that neural network, go ahead and do any of that learning stuff from any of the other sort of neural network learning things, just add them on top of that. Right? There's no reason, like you could just treat the neural engineering framework as a really interesting way of initializing connection weights. and then go on and do whatever the heck learning you feel like. That would be one possible approach. So if I wanted to, I could just sort of say, all right, that's it. That's all we have to say about learning. We're done. I want to spend a little bit more time there because I do think there are some interesting things that we can say because we have this different perspective on learning from the neural engineering framework, or have this different perspective on neural networks from the neural engineering framework, and maybe that sheds slightly different light on learning. But as a first pass, anything you have ever heard about neural networks learning, sure, go ahead and add them into these networks, no problem. Okay. So let's basically start with that. We're going to start with the standard thing that people do with neural networks, which is supervised learning. Okay. And this is a sort of situation where you have a big giant set of data. So you have, all right, here is an image, another image, another image, and another image. Those are my inputs. And for each of those inputs, you have a category that it's in, or you have some label or some desired output. So for instance, this picture here might be put in the category dog. This picture might be the category cat. This picture might be category, I don't know, bird or parrot or whatever these are. So you've got a bunch of images. Each one you have a category, and I can turn that category into this sort of, okay, so one category is going to be 001, another category is going to be 100, another category is going to be 010. Those are my three categories. And my inputs are these images. Now the first thing you'll note is this is exactly what we have been doing all throughout the course, right? This is, I want a neural network to approximate a function. My input is an x. This is a vector. I mean, it's a really high dimensional vector because it's an image, but fine, it's just a vector. Right, my input, all right. So I have an image and I have an output, I have a y. So this is exactly, we could use exactly what we've been talking about in the course so far. Fine, just instead of randomly sampling x and having some function that we sort of evaluate x at that function, we get what the output is. Okay, cool, we already have, here's all my x values, here's all my output values. I can go ahead, take these x values, feed them into my neural network, get the activity, get this big long list of my y values, and that's my targets, that's my functions. Solve for my decoder, I'm done. All right. Of course, for this particular task with all of these images, what generally ends up being the case is it turns out that a single layer neural network would have to be ridiculously large in order to do such a task, especially if you had randomly generated encoders. Okay, but this is the sort of task that a deep neural network sort of system would be doing. But let's take a close look for this sort of problem. How is it that these sorts of traditional supervised learning networks work? What they tend to do is you take one of your images, you feed it into your network, and it produces some output. Okay. And so maybe we just randomly generate that in our initial set of connection weights, or we've done some sort of nice solving, whatever. We take those initial sets of connection weight, we take that image, we get an output, and this is our output. And say this is the actual output, but say this is the desired output, because, I mean, all right, this is supposed to be a parrot. And then the idea behind these learning rules is what they're going to do is they're going to say, well, look, there's some difference between the actual output and my target output. We're going to compute that difference, and then we're going to use that difference to change our weights. Okay, that's the basis of pretty much all supervised learning algorithms. Cool. So how are we gonna, what are we gonna do? How are we gonna change those weights? Because eventually, after we do this a bunch of times, right? After we've done this a bunch of times and say, okay, we change these weights. Eventually, we say, okay, we're done training. And then once we're done with that training, now we say, okay, now we're going to go deploy this network. I'm going to go, make use of it. When I'm making use of it, I'll be feeding in new inputs. or perhaps inputs that are the same as the old inputs, whatever. And then I'll get some output, and that's the output that I'm going to go then and use in some other system. I definitely want to highlight that there's a big parallel here between what we do in the neural engineering framework. This training process, this is kind of like us solving for the decoders, okay? Just sort of an iterated version of it. And then this inference process is kind of like what we do when we're running our model. Okay. Now, in deep neural networks, there's a lot of really fun, wacky math going on in order to figure out what ways to change weights given this error. This is what the backpropagation learning algorithm is all about. There's also some really important things when they do that backpropagation learning, that they'll do things like, instead of feeding in one image at a time, they will feed in 1,000 images and then do all this big computations, do all this sort of thing for all those thousands of images, and then do a weight update. So that's the sort of batch learning approach. There's also a lot of interesting things about you have to feed in your images in sort of a random order if you want it to be sort of robust in all sorts of situations. So there's all sorts of weird technical things like that, all of which are sort of like, okay, there's no way brains do that, right? Brains do not do all of the wacky math that backpropagation does over many, many layers. It might do something similar. And brains do not do the approach of, all right, let's take 1,000 different inputs and then I'll learn. But that's still a totally useful tool in order to get good connection weights, the same way that solving for decoders is also a totally useful tool for finding connection weights. Okay. And in any case, through both of those things, once you've got your connection weights, now when you're actually in the inference process of just sort of saying, okay, here's a new input, give me an output. Now we're in a domain where everything is exactly the same between deep neural networks and the NEF. But I still want to spend a little bit of time figuring out, okay, what's going on with this weight update. Okay. I want to start with a little example here, just to get some sort of interesting initial intuitions about this. Here's just to get a little bit of an intuition. Here's a really simple, I don't even want to call it a neural network. Here's a really simple function, really simple thing with some weights and some inputs. So it's of the same form as a neural network. It's a kind of neural network with like two weights, W0 and W1. And the reason that I'm saying that that I'm picking something with two weights is that lets me visualize it. Right? Because if I've only got two weights in the whole system, then I can at least plot it. And at every point in the space, I can say, oh, how good is it at that point in space? What do I mean by how good is it? Well, what's my training data? In this particular case, my training data, my input is some value x. My target value is some also scalar value, and I'm putting a little plus sign indicating, okay, these are my training points. Oh, sorry, these are my training points. Okay. And I've randomly generated those training points based on this dotted line curve, plus some noise. Okay. So this would be kind of like, all right, I'm trying to train up a network to do compute x squared, but I'm also including a bit of noise in the training data, just because in real life you might have noise in the training data. And then generally what happens is you start your weights at some random value. So if you want to do an online learning process, then what you would do is you would set your weights at some random value and see what it does. Okay, so I set it to some random values. So, okay, apparently the random values are 2.5 and 2.5, which is this point here in the space. Or sorry, I guess, yeah, 2.5, somewhere around here. And then we go and do some math that says, well, if I were to change those weights, how would that change how good my function is? And how good my function is just evaluate this function at each of these input points, okay, and see how close is my output to the target values. All right. How would we figure out how to change our weights in order to do that? Well, just jump back here. All right. This is a minimization problem. Right. This is saying, all right, how good is my function, or what does my function say? So across all of my sample points, what does my function say the answer is? What is the actual answer? Call this mean squared error. And what we're trying to do is we're trying to find the weight that minimizes this. Okay. Again, this should start to be sort of a somewhat familiar problem. If you want to know what way to change your weights in order to improve this, one way to do that is called gradient descent. And this is sort of the basis of the backpropagation error learning rule. All you're doing is you're taking that error function and you're doing the derivative of it with respect to your weights. And that tells you, all right, if I change my weights, which direction should I change my weights in order to reduce my error? Okay. So that's sort of the core idea. So I do that. That tells me to change my weights in this direction, for example. Well, sorry, I guess that tells me that that direction is the way that my error increases, so I should change it in the other direction. That's the derivative of the error. Fine. All right, so I change it there. That tells me to change the weights, and I sort of move a little bit in that direction. I change the weights in that direction. Now it's this curve. Maybe it's a little better. Do it again, 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 do it again. Oops. Okay. And eventually, we get a set of weights where the derivative ends up being kind of close to 0, so it stops changing, so we stop changing our weights. And this is sort of as good as we can get, given these sample points. Of course, in this particular case, I could have just found those sets of weights just directly, just by doing the least squares minimized, by just doing the matrix inversion, doing the same sort of solving that we've been doing for solving for decoders, because this is a problem of that same form. So I could have just solved for decoders, and that would just tell me exactly that answer. Now, the reason backpropagation learning exists is if you have a neural network with multiple layers in it, then you can't just use least squares minimization to just find this answer. But anytime that you're only having one layer of weights, it turns out you can always just solve for that using the least squares minimization approach. But that's the sort of the intuition behind all of these gradient descent sorts of learning rules. These that you're just going to sort of gradually change your weights and then eventually stop. Cool. All right. Oh, right. Of course, it does turn out that if my, it's highly dependent on what that ground truth was, and if it turned out, I only gave it values of x between -1 and 1. If I wanted, if I was then like, okay, cool, I've learned something, it'll probably do a good job of indicating what else to do in between -1 and 1 for sort of other points. But if it turned out that my ground truth was a curve like this, and I just never gave it data out here from this, with an x of 2 or x of 3 or -2 or -3, of course, there's no way that it would have learned that. So that's the standard problem that neural networks tend not to generalize outside of the range that they were trained on. Again, similar in the neural engineering framework, we have our functions that compute well. We have some radius, and this is the domain over which we have solved for our decoders. Don't expect to do a good job outside of that range. Same sort of idea. Okay. Now, one cool thing is that learning rule of take the derivative, turns out to have a really nice form. Okay, so if you actually go and work out what that, take the derivative of the error with respect to the weights, and go and work it all out. it turns out that it just ends up having that the change in the weight that you want, so the derivative of the error with respect to your weights, okay, I'm using D for the weights because I'm just thinking of these as decoders right now, turns out to be of this form here. Okay? It's this sum here, which is the actual decoded value. So this thing here, that is just the decoded value. All right, well, okay, let me start over. This is what the form of the error is, right? We have the decoded value, this thing up here, which is just my activities of my neurons times my decoders, minus my desired value, and we square that, right? That's my mean squared error thing, and then people toss this 1/2 out here because that's going to cancel out nicely in the future. And the nice thing is scaling your error by 1/2 doesn't change what the best decoder weight is. If I take the derivative of this with respect to D, what do I get? I get, all right, I still have this term here, so the 2 comes down, the 2 cancels with that, and I keep that whole term there, but then I multiply it by the derivative of the inside, this is chain rule, multiply by the derivative of the inside, derivative of this with respect to D is just this activity. Let me get this activity so that gets put out there. So what this means is that this first term here, that's just my error. That's just the difference between what I'm decoding out and my target. All right, so that term there is just the error. And so this is just the error times the activity of my neurons. Okay. That is what the, if you were doing backpropagation learning, doing gradient descent learning just in general, that's how you should change your weights. Okay, take your error, multiply it by your activity. That tells you how, of that particular neuron. That tells you how much to change that weights. This is a really common learning rule. It's called the delta learning rule. It's sort of the basis of almost all neural network learning rules. You can trace it all the way back to the perceptron days. So this is sort of the canonical initial starting point for almost every learning rule. Okay. And so that's what we're showing here. If I have a bunch of neurons and I'm trying to decode out a value, my learning rate, or my learning rule, or one simple learning rule that we often want to start with, is compute your error, multiply your error by the activity of a neuron, put in some learning rate, so that's how big a step you're going to make, and I need a minus sign because I want to decrease the error, not increase the error. And that will tell me how to change my weights. Okay, so that's the standard delta rule. Now, in brains, we don't have this Y thing. In brains, we have a group of neurons representing Y. And the way we get these connection weights is by taking our decoders in the neural engineering framework. The way we get our connection weights is we take our decoders and we multiply them by the encoders and the gain. Right? That's how we get our weights. So, if I want my learning rule, if I want the same effective learning rule as this delta rule, but I want it to work over here where I've got connection weights, well, all I have to do is take the normal delta rule and take that error term, multiply it by the encoders and by the gains. All right? So I'm just going to do exactly the same process. So this system should do exactly mathematically the same thing as this delta learning rule, but it's just going to work where I have neurons in my outputs. I have a distributed representation of my values, not just in situations where I have a single scalar. Right? So we're generalizing the delta rule to work in situations where everything's neurons. Okay? The term that we've used to define for this particular learning rule is the prescribed error sensitivity rule. The reason that we're calling it that is that one way to think about what we're doing here is we're using this error signal some error signal coming in here, and having this computation tell us how sensitive to error should each of these, or how sensitive to what sort of error should each of these connection weights be. Okay. Anyway, it's where the term comes from. We generally just call it the Pez rule. Conceptually, it's exactly the same as delta rule. We're just doing this extra multiplying by the encoder and gain in order to make sure that we're actually modifying connection weights instead of modifying decoders. Now what this does is this lets us use this learning rule inside a larger system where everything is neurons. Okay, because the normal delta rule is only going to work in situations where I'm just looking at my output and not really having that itself be in neurons. Cool. All right, what can we do with that? Well, let's show some examples. So I'm going to start with a situation where all we're going to do, where we're just going to learn a single set of connection. We're just going to learn a function. Okay. We're going to initialize this to sort of the 0 function. So all these connection weights are initially going to be 0. We can then take whatever's decoded out of this group of neurons, and we're going to want some, and then we're going to have some function that we're going to need to have the error be computed somehow. We need to have some way of having this error signal in order to indicate what it should be doing. We're going to do that manually. We're going to say, all right, we're going to just put in some function here such that I know, given this, or given x, what my value should be. We're going to do that subtraction, feed that back in. That's going to give us our connection weights. It's going to tell us how to change those connection weights. All right. The place I'm going to get these, so instead of coding up all these examples live, I'm going to be using all the examples from this repository here. This is my GitHub account, Nengo Learning Examples. So that's where all these examples are going to be coming from. And let me just run Nengo and pull that up. All right, now I'm going to open this up inside Nengo Learning Examples. We're going to do a learning 1 as an example. There we are. I just want to highlight, okay, so we are building up a Nengo model, same way that we've shown in the examples before. Is there anything new? So one new thing I'm doing here is, instead of saying the stimulus is like node 0, right, and saying, all right, just feed in 0 all the time and I'll move the slider around. Instead, I'm specifying a function, and so that is just going to cause it to automatically move the slider up and down as a sine wave. Okay, just because I can't be bothered to wave the input up and down a little bit. I'm taking that input, I'm feeding it into this group of neurons. I'm calling this group of neurons for presynaptic. This is just indicating this is the group of neurons before, I'm going to be learning here. I've got this group of neurons, I've got this group of neurons. We're going to call these the presynaptic group of neurons. This is the postsynaptic group of neurons. So the connection weights that I'm learning are the ones between pre and post. Okay. So I'm feeding that into this group of neurons, exactly the same way as we always do. I'm going to make a connection from this group. Right, I've got this second group of neurons, that's this one here. I'm going to make a connection from this group of neurons to this group of neurons. And this is where we're going to get something a little bit new. There we are. So I'm going to make this connection. It's going from pre to post. I'm going to, when Nengo solves for that connection, it's got to do something to get those connection weights. I'm going to start it off saying, all right, do this function. Do the 0 function. This is the function that just outputs 0 all the time. It's going to go ahead and solve for those connection weights. As you can guess, it's going to end up deciding that all the connection weights should be 0, because that does a pretty good job of decoding out 0. So that's all the same stuff we've seen before. This is the new line. Okay. This is saying, on this connection, please implement this learning rule. There's a bunch of learning rules that are built into Nengo. One of them is this PES Pez rule thing. Okay. So we are going to get that have that learning rule. But in order for that learning rule to work, I need to have something that feeds in an error signal. And I'm going to use another group of neurons to encode that error signal. So here's a group of neurons that's going to be representing my error. Okay. And what we're going to do is we're going to take this group of neurons. I'm going to take whatever was in this group, pass it into here. Now it's just with an identity function. Okay. So that is this connection here. Okay. Please pass that from post to error. Then I need to sort of define some sort of thing that's actually getting me the correct answer. Okay. At the moment, the function I'm going to learn is just x. I'm going to make a connection from this thing to here, to this input, to my error, that is, say, doing this function. Now, of course, this function itself, this is not neurons, right? So it can't use, so Nengo can't do the, oh, hey, look, here's a function. I'm going to go ahead and solve for decoders in order to do that function, because there are no neurons here. And so what Nengo does in this case is it just says, okay, well, these aren't neurons, so I'll just compute this function on it. Just, every time step, whatever the value is, I'll compute this function and pass that value along. Fine. So that's going to be getting the correct answer, or sort of the error should be being fed into this group of neurons. Oh, of course, I will multiply that by -1 because I want this group of neurons to have the difference between those two things. So what we should actually get is what are we currently representing minus what we should be representing. That's going to be fed into this group of neurons. And then the key step is I'm going to do this line here, which says I'm going to connect from this group of neurons to my learning rule. And that's just what the Nengo syntax is going to be for making a connection that is actually just sort of feeding data into a learning rule. Okay. One really nifty thing about the prescribed error sensitivity learning rule is the value that's being coming out of this group of neurons, since we solve for a decoder to come out of this group of neurons, what this error signal is, what you end up with is a learning rule where each individual synapse just needs to know how much total input am I getting from this population and what's the activity from this population, and that is sufficient to make the weight change rule. Okay. So everything becomes a local learning rule. This is all information that is available at a synapse. So it becomes a biologically plausible learning rule. There's no global information needed anywhere, and we explicitly have a group of neurons that's representing the error. I kind of like that as if I'm going to be sort of studying how biological systems learn, because I also want to make sure that whatever learning process I'm designing, every single step in it is something I know how biology could do. Okay. So this forces me to say, all right, biology is going to be representing the error somehow. It's probably going to do that with a group of neurons. Go ahead and make this work. Okay. I'm then going to add one extra little fancy thing in here, just to make my life easier as a demonstration. And that is this group of neurons here. It would be nice to sort of see what happens if these groups of neurons were taken away. Right? So once it's learned, these groups of neurons probably shouldn't be important anymore. Okay. So I also want it in a way of I want to be able to suppress these neurons in order to make it clear, in order to say, okay, don't learn right now, right? So that I can go and observe the system when it's not learning. So basically all I'm saying there is I now have a slider that's called stop learning. If this is a 1, what I'm going to do is just massively inhibit all of the neurons in here so none of them are going to be firing. If none of them are firing, then that means whatever value is being decoded out of those neurons is going to be 0, because whatever these decoders are, 0 times anything is 0. So that should mean that if all of these neurons are suppressed, there will be no weight changes along this connection. Okay. My syntax for doing that in Nengo, I'm not sure we've actually shown this before, basically what we want to do is we want to be able to bypass the whole encoder-decoder thing that Ningo normally does. The way you bypass in Ningo is if you refer to error.neurons. So if I'm going from stop learn, which is this thing here, I'm going to say I'm just going to directly connect that to the neurons. But in order to directly connect it to the neurons, well, there's like 100 neurons here, and I've got one value, so I've got to be explicit about what to do with that. And so I will give it a 100 by 1 weight matrix that is all minus 10s. Okay. So that's a big giant weight matrix that just simply says, all right, that's what we're going to do. We're going to bypass encoders and decoders. Don't worry about it. We're just going to massively suppress the activity of those neurons. Just to let us turn off the learning rule. Whether or not biology actually does that is a whole other question, but it's more right now for our process of saying, I just want to make sure I can turn off the learning. All right, with all of that said, what happens when I run this thing? Okay, here's my input moving up and down. Great. Here's that presynaptic population. It's doing a perfectly good job of encoding that information because this is all done with normal neural engineering framework stuff. So that's all stuff we've seen over and over and over again in this course. My postsynaptic population is sitting there representing 0, and that's because this connection here was initialized to compute the 0 function. So it's doing a perfectly good job of doing that. These neurons here are not firing at all because I've massively suppressed them. So let's get rid of that suppression. Let's let those neurons start firing. Okay, they're now causing these connection weights to change. Eventually the connection weights change. My error is now pretty close to 0. All right, my presynaptic to postsynaptic seems to be doing a good job. Let's go suppress these neurons. And now we have exactly what we're looking for. We have learned the connection weights that compute the identity function. This was basically just a slow way of doing the solve for the decoders. And indeed, if you did a learning rule with an infinitely small learning rate, and you did it for an infinite amount of time, yes, this process would converge onto the same, and if noise was in the same sort of properties that we were as assumed, that would converge onto the same answer that we're solving when we just solve for the decoders. Okay. So any of the situations where we've solved for decoders in this course, we could set up something like this that goes ahead and trains it and does it very, very slowly and and varies the input over the space that we want it to. And we would end up the same connection weights if that's what you're really interested in. I just find it much more convenient to just solve for those connection weights rather than doing this. But it's also very good to show that it can solve, that we can learn these things online. It's also important to show that this works for more than just the identity function. So let's do x squared, why not? Now again, we're computing x squared manually, not in neurons, across this connection here. So we're not saying anything about where this answer comes from. We're not saying anything in this model whatsoever about where this correct answer comes from. All we're saying is, hey, look, I've got one input that's x, I've got another input that's going into here, which is what the correct value should be. That's all I need for this sort of learning to work. Again, I'll try that. The only thing I've done now is changed what inputs will be fed into this group of neurons. I haven't changed anything about my network. All right, let's go let that happen. Let that run for a while. And we get our nice little computation of x squared. Cool. All right, so we can learn functions. So this nice simple little learning rule will let us do that. What else can we do with this learning rule? I just want to make sure that's all there. Okay, I have covered that. Right. Oh, sorry, I forgot to mention, it is worth pointing out that yes, with this more complicated function, it ended up learning a little bit more slowly. We might, in a more complex situation, I might need to decrease my learning rate. things like that. There is, of course, the open question. This sort of learning only makes sense if you have some sort of story about where this error signal would be coming from, or where this correct value would be coming from. I can get my error signal by subtracting what I'm doing from the correct answer, but in order to get that, I'm going to need to get that correct answer from somewhere. Now, the nice thing is, there are some situations where we might actually be getting a realistic correct answer from somewhere. And so let's do, and so I guess one sort of classic situation where this might be, would be the standard story of classical conditioning. So classical conditioning, this is the Pavlov's dog sort of experiment. This is the sort of way this is normally broken down. So fine, if I give a dog food, it starts, or if I show a dog food, it starts drooling. Fine, okay, that's just sort of built in. We assume that there's some sort of built-in system that does that. But then if I do I ring a bell and then present it with some food, eventually after I do that a few times, I can just ring the bell and it'll start drooling. So this is sort of a classic experiment. Okay, that seems like learning. Right? And seems like something, can we use the learning rule that I just talked about to do this sort of task? When the people run this experiment nowadays, they tend, instead of doing it with food and drooling, or with ringing bells, they tend to do it with, all right, turning on a light or something like that. So that's in this example here. It's a mouse instead of a dog, but whatever. And they're turning on a light instead of a bell. So, how are we going to set that up with the components that I've just shown? Well, let's open this up with conditioning. Okay, what are we doing here? So, the first thing that we have is we have this unconditioned stimulus thing. We have this thing that's already built in, which is when I give you food, you start drooling. So we're going to assume that that is something that, say, okay, we're just going to build that with normal neural engineering framework approaches. We're just going to go ahead and build that set of connection weights. Okay. But then we're going to say that there's some other input. So this is, so the unconditioned stimulus, that's the food, and then we're going to have this drooling thing happen here. But then there's going to also be a whole bunch of other stimuli out there. So, I don't know, my vision, there's all sorts of other sorts of sensors that I have. Maybe it's ringing bells, maybe it's bright lights, things like that. This is all going to get fed into some group of neurons. And initially, there's no response to any of this stuff. Okay, so this connection weight here, from the conditioned stimuli, the stimuli that we're going to be learning about, to the conditioned responses, so what responses are going to be generated by these things, initially that is going to be the zero function again. So all those connection weights are going to be 0. And now what we're going to do is we're going to say, okay, let's make my error be the difference between these two things. Okay? Whatever conditioned response I do should be the same as whatever unconditioned response I have. Okay? So here's what I'm saying is my training signal, where I'm getting my error from, is from some sort of hardwired physical responses. Okay. That's going to give us our error signal. Again, I'm going to apply that error signal to these connection weights. And again, I'm going to have this ability to turn learning off. Okay, so let's stop learning. All right, so what am I doing in this experiment? Let me actually reset this completely. Turn off learning. There we are. Okay, so the way I'm setting up this experiment, and what I'm plotting here, I have let's go to a larger screen. I have the unconditioned stimulus. So this is going to be my presenting food. This is going to be the response from presenting food. This is going to be my ringing a bell, and this is going to be response from ringing the bell. Okay? So initially, I'm ringing the bell, nothing happens. Okay. Just a second. Why is my learning happening? Sorry. Let's restart this. Start this again. Okay. We've got learning going on. It's fine. So initially, absolutely nothing is happening. Right? My condition stimulus. Just to make life complicated in this case, I'm going to have like 3 different types of food, 3 different types of drooling, and 3 different types of bells that I'm ringing. Okay, just to show that this will generalize to learn more than one thing at a time. And those are just drawn in different colors. So initially, I present blue food and I get blue drooling. I don't know, whatever. Present some stimulus, I get some immediate instinctual response. When I presented the blue ringing of a bell, there was no response. However, once I've got a response, it goes, oh, hold on a second, I should do some learning. Okay, and it starts building that up. Okay, that's that error signal being applied. It goes, oh, okay, my error is now non-zero. I should go do something about that. Okay. Of course, it's now gone and done something with that. Now it's like, okay, making a response, but now it's like, well, hold on. It's, oh, shoot, right, okay, but now there's no stimulus. My unconditioned response is there, so this is what I should be doing. Now I'm wrong. I got to go unlearn whatever the heck I did. It still hasn't figured out how the right way to associate this with the stimulus, because there's all sorts of things. It changed a whole bunch of weights at once, and it was like, okay, maybe those were the wrong ones, and started changing them back. I do the same thing for green, do the same thing for orange, and then I repeat this, and repeat this, and what you see, hopefully over time, is we pretty soon get to a situation where now, when I ring the bell, ring the blue bell, I get a response, and it's somewhat stable. It's still like, okay, hold on a second. There's no actual response yet, so maybe I want to get rid of this. But then the actual response does come, and we still continue the response, and we drop off the response pretty quickly. Right. So all we're pointing out there is here's a situation where we can get something an awful lot like classical conditioning. And this is a situation where I can make some sort of story about where this error signal is going to come from. Okay. Cool. Again, everything else is exactly the same. I think the only other new thing in this code is I'm also showing here how to adjust the learning rate. So there was a learning rate parameter on the learning rule, and yes, I basically cranked it up as fast as I could in order to actually show the learning in these processes. All sorts of fun experiments could be done in order to figure out, okay, what are good learning rates in order to match biological behavior in these sorts of tasks. But it's a nice, simple model of conditioning that gives you a nice place of where all these learning rules could get their error signals from. What else can we do? So that's one interesting possibility. Yeah, let's go up to this one. I also want to show this example. So here's a very similar one, but instead of conditioning, this is more of a model of, there's a phenomenon in the brain where as you're learning to do a task, initially you do it very slowly, but then it sort of starts to become instinctual, starts to become kind of immediate. So one classic example of this would be when you were learning to add, and you started with doing 3 plus 4. Initially you were doing, okay, 3 plus 4 is 3, 4, 5, 6, 7, and the answer is 7. That's a slow process. Eventually over time, if someone just says 3 plus 4, you just immediately say 7, because that's the right answer. Right? It becomes a direct process. Okay. So one of the master's students in our lab a few years ago did a nice model of exactly that task of learning to do addition, that sort of consolidation process. And that's also, in order to do that consolidation process, the basic model ended up being exactly this learning rule. And what we did there is build some system, take that sort of a long processor that goes through a bunch of different steps, that uses, say, the basal ganglia and all the symbol representation stuff that we were showing in previous classes, and goes and does that slow and laborious step, and have that produce some output, but then use that output as your training signal to train up a faster system. So that's what we're going to do here. I'm going to have some really slow, long system here. Okay. In this particular case, just for simplicity, I'm not doing a big, giant, complex neuron model. All I did is I'm just actually computing the function, like the identity function, but I'm just putting a ridiculously long time constant on it. So it's a very slow calculation. Okay. Fine, I can do that. So this value here is going to follow whatever my input is, but just very slowly. Okay. And then what I'm going to do is I'm going to also learn a faster system that has a fast time constant, and I want my error to be the difference between these two things. I'm going to do one kind of nifty thing, in that when I make these connections into the error signal, I'm free to choose a time constant of those. And so one thing I can do is I can choose my time constant such that I'm getting kind of a slow version of this signal. So really what I'm doing is I'm sort of subtracting whatever this value is now from whatever the value of my target was 200 milliseconds ago or some time ago. Settle it. And I'm trying to say there's no reason that this error calculation has to be the difference between these two values right now. I can also do some computation along here in order to delay that signal, or compare what the values are at different points in time. Again, I can do that because we can build that up with the neural engineering framework stuff. So again, we're basically using the neural engineering framework to do all of the rest of this, but then we're using this learning rule to learn this connection weight here. Okay. Now what's that going to look like? So I've got learning turned off right now. My target value is this green line going up and down. So my input is this smooth blue line. My target value is this green line. At the moment, it's clearly just not doing anything. This green line is sort of a really slowed down, delayed version of this blue line. Okay. So then what I'm going to do is I'm going to say, all right, let's turn on this learning. Okay. Again, right now I'm inhibiting this error population, so there's no learning going on. I'm going to get rid of that inhibition. Now that learning is going to happen. So the blue line is what is being learned. The green line is what the slow, gradual system is doing. The blue line is trying to learn that, and we get a little bit longer, and we're now in a situation where the blue line is doing a reasonable job of doing what the green line does, but before the green line, because it's a faster process. So yeah, if I let that run a little bit more, let's say the blue line is doing what the green line does, but just a little bit before. So that was something that we published as a model of this consolidation process. Because again, this is something that's seen in brains, that you do something initially very slowly, and then you use the brain itself to train up a faster version of that. Cool. So that's also something you do. Again, this is all just about coming up with different ways of computing this error signal. Okay. Awesome. What else can we do? That's the conditioning model. That's more graphs of this. Okay. Let's do something else. It's going to end up being a very similar learning rule, but now what I'm going to do is I'm going to take something from control theory, which is an adaptive controller. What's that? Let's say I'm moving an arm back and forth, and I have some position that I really want the arm to be at. The command that I'm sending to the arm is how much to push it left or right. And yeah, and I have some desired position that's going to be at. Of course, the arm has some momentum. There's gravity on it. There's other forces on it. And what we're trying to do is compute that. Is trying to learn how much pressure to put on that arm. There's a standard algorithm from controlled as to how to do this. And the standard algorithm, sometimes called a proportional controller or a proportional derivative controller, is saying, look, what we're going to do is we are going to take what the difference between the positions are, multiply by some value k, feed that to the motor, but then also take the difference between the derivatives, feed that to the motor, feed that to the controller, and then have that be the output. What we're going to do in this system is we're going to say, all right, let's also add in a learning system that'll actually learn, is there some function between the state of the arm and my action that will end up doing a better job? Okay, we're going to learn that. That was probably very confusing. Let me actually pull up a real example. So I'm going to go to the control example. Yeah, we got time. Let's go through this carefully. So let me just start with what I mean by this system that I'm controlling. Okay. So I've got some, I don't know, we'll call it a arm or a pendulum. It's just this black line. Okay. It's just a stick with a joint right here at the center. And there's some gravity that's causing it to swing back and forth. Okay. The blue line is where I want it to be. Okay. When it's up here, gravity pulls it down. It goes really fast. It goes back up. Gravity pulls it down. It goes really fast. Okay. And the purpose of my controller is I want to feed. I want to apply force onto this. In this simulation I've got right now, I don't have anything controlling it. This is just the free-flowing pendulum. There is no gravity. There is no nothing, or there is no neural network doing anything. Yes, there's gravity, because we can see it there. If I want to try to manually try to be the neural network, so I might do something like, oh, I don't know, push it that way. Oh, no, okay, no, slow it down. Oh, no, now it's going that way. Right. This is just how much force am I applying. Right. So this is the thing that the neural network is supposed to be learning. All right, and you can see that if you apply too much for it, it's just spinning around and things are bad and it's really hard to do this. All right, so the really simple algorithm that people normally start with is, all right, well, look, what's the difference between this blue thing and the black thing? If I'm too far to the right, then push it to the left. If I'm too far to the left, push it to the right. And, scale that by how far away I am. All right, so let's pull up that example. So that is called a proportional controller. Okay. And we have some constant here, which is how you take the difference between where I am and where I want to be, and you multiply it by 1, and that's the amount of force you're going to apply to the pendulum. Okay? And that's what we're doing here now. And you can see it wiggles back and forth. Why does it wiggle back and forth? Well, because of momentum, right? Like as you push it to the right, eventually, when it gets right where it is, it's like, cool, all right, I don't need to push it anymore. But it's moving, so it's going to keep going, and then it's going to go back. Right? If I move my target, I get this sort of behavior. So, okay, so first of all, I put it here, and it's like, okay, this is a problem. It's just going to waver back and forth. So that's one problem with just a proportional controller. If I put it over here, all right, it wavers back and forth, but you'll notice it's spending a lot more time below than above. This is just bad. Okay. If I do something like decrease this, the weighting factor. Oh, I've decreased it too far. Let's decrease it to there. Put my target over here. We're still going to get this sort of pretty big problem. Maybe put it over here. Yeah. All right. If I increase it, all that's going to do is just going to make it go wobbly even more. It's just going to wobble faster. All right. We got to 10. Ah! Now it's just going to no. All right. Proportional controller on its own doesn't help, or has issues in those sorts of situations. The standard thing to improve from that is to say, all right, let's do a proportional derivative controller. And this is saying also, don't just do what's the difference in your position, also do what's the difference in your derivative of your difference in your velocities between where you want it to be. All right, so first of all, that now nicely gets rid of the wobble. Because basically, as you're getting closer, it starts going, well, hold on a second, my velocity is too big, my velocity is supposed to be 0, slow things down, and so that'll slow you down as you're getting closer to where your target is. But we now have a new problem. And that new problem is gravity. All right, so this is where the army is. It knows there's a difference between this and its desired target. All right, and so the system is applying some torque to the left. It's applying force to the left to try to get the arm up. But gravity is pulling it back down. And these two things are nicely canceling out, so it doesn't go anywhere. All right, and if gravity is more, so I've got a little slider here that lets me increase the mass of the arm itself. Now, the more gravity is, the more this is going to pull down. So that's the difficulty with a proportional derivative controller or PD controller is, all right, there's extra force pulling you down. All right, or you need something to deal with that sort of offset error. The standard thing that people do in order to deal with that problem is called a PID controller. What's a PID controller? Well, what that's doing is that's also saying, hey, in addition to that proportional and the derivative system, what we're also going to do is we're going to see what our error is, and we're going to compute the integral of that error. I'm going to put that integral here. Okay. I totally forgot to mention this. All these things about computing the derivative and computing the differences, in this particular case, I'm doing them all with neurons, because these are all things that we know how to do with neurons, so we may as well. Right? So again, computing the integral, we know how to compute the integral. So all of this particular neural network that we're building, I am all doing it with neurons. Whether it's important to do it in neurons is a separate question. That's more sort of proof of concept. Yes, we can. But this is the integral of the error. And then what you do is you take the integral of the error and you multiply it by something, and that's going to be extra force that you're going to add on. So now, if I put the arm over there, all right, there was some error that caused me to add some more force, and I've compensated for it. Put it back there. And now it's learned, oh, okay, cool, the error should be this. Okay, so it's learned how much extra force. Oh, hold on, I gotta be careful there. I don't want to call this learning because I'm not changing any connection weights. But effectively what this integrator has done is it is representing the error from the past that's saying, okay, this is how much extra force I should be applying right now in order to make myself stay at the position that I want to be. And that works. And that works. Now, you may have noticed something when I switch this value from two different locations. Right. First of all, there's that big wobbly behavior. I say, okay, I'm supposed to go here, and you get this big giant wobble. I'm supposed to go over here, you get this big giant wobble. Okay. I can play around with that wobble by adjusting these sorts of constants. Fundamentally, it's usually going to be there, just how much I'm going to scale that by. But the sort of in one place that you can sort of think of where the cause of that is during that time of that transition, it needs to learn a different offset weight. Right? It needs to learn that over here, I'm supposed to be putting this much extra force on. But when I'm over here, I'm supposed to be putting this much force on. Okay. What would be nice is if we had a system that could actually just learn that function. Because that just sounds like that's just a function, right? That's just, depending on what x is, depending on where my angle is, how much extra force should I be applying? In this particular case where we're doing it with an integrator, all we're doing is we're just storing one value in an integrator. Right? We're not actually really learning anything. We're not changing any sort of how it responds in different situations. This is all just dependent on its current past history. So this is the intuition that we're going to come up with. Okay, hey, look, let's put in a neural network. Let's put in some sort of learning rule that learns this function, that maps from this angle to this sort of thing that we would normally be doing as an integrated term in a PID controller. So what's that look like? So what I've got here, so I still have the PD part of the controller. So that part is still exactly the same. But now what I've got is I've got one more neural network that is just, taking that, the context information. So by context, I mean, okay, what information is going to use to figure out how much force I'm going to be putting on. In that case, it's just going to be, actually, what did I do here? I think it is both the position and the velocity of the pendulum. Okay. So that's being fed into a neural network. And then I'm taking the output from that network and just adding that onto my control signal. Okay. I'm going to put a learning rule on that network. And my error signal, the thing I'm going to use as my error signal for this learning rule, is a little bit surprising. What I'm going to use for my learning rule is the command I'm currently sending to the motors. That's a slightly surprising thing the command that my PD controller would be sending to my motors right now. Okay, so the actual command I'm sending is what is my PD controller doing plus what this learned signal is doing. I'm going to use as my error signal what would the PD controller on its own be doing. You can get some intuitions for that. Well, certainly, like, well, if everything was working great, then the PD controller would be outputting a 0, and so my learning would stop. So you can get some intuitions for that. The actual math proof that says that this is a stable thing to be fed into a learning rule is actually surprisingly complicated. This comes out of work from Jean-Jacques Slotine in the 90s in something that's called adaptive control. It was initially done, phrased in a way that wasn't set up to be a neural network. One of the things that we did is we sort of showed that this particular process where we would turn this into this neural network learning rule becomes the same sort of thing as the Jean-Jacques Slotine adaptive motor control stuff. And so that's why we were able to just use his math proof saying that this is the right error signal to use. But we're going to put that in as the error signal, and we're going to see what happens. One extra thing I'm going to do is I'm also going to plot the function that it learns. Okay. Again, all we're doing is we're changing decoder weights. But once you've got those decoder weights, you can also sort of just plot, okay, well, what is that function that it has learned? Okay. I'm moving the pendulum back and forth just to do that. So first of all, we can see it's doing a good job of going where it's supposed to go. And this is the function that it's learned. It's learned that, so what's my position of my arm? If I'm here, don't add on any extra force. If I'm all the way to the right, well, you got to compensate for gravity. If I'm all the way to the left, you also got to compensate for gravity. And then the cool thing is, so this is now working nicely, moving all across the physical space. If all of a sudden I do something like, let's increase the mass of the pendulum, or the mass of the arm that's being moved back and forth, it takes a little moment to compensate, and you can see it's now learned a slightly different function. Now it's like, okay, now this is how much force I'm going to need to compensate. Pull it back, and it'll unlearn that. Okay. Again, it's a situation I can use exactly the same learning rule. I'm using a very different way of computing the error signal, and now I'm getting a sort of useful behavior out of it. Cool. That actual system is something that we've gone on and actually applied in real physical robots, and shown that it can actually start to learn things like it'll learn to deal with wear and tear at the joints. or it'll learn to deal with unexpected weights on the arm itself. Yeah, and that's been one of the fun products that's come out of the Applied Brain Research spin-off company from the lab. So that's sort of a fascinating, really strange sort of application of this, and it came out of, initially we built this sort of model as a model of the adaptation in the motor control systems in mammals. So this came out of one of the PhD students in the lab. Was initially this is Travis Wolf, was doing a lot of motor control work and modeling the motor control system, and this part turned out to also maybe have interesting industry applications. Cool. All right. So that's another thing that you can do with the same learning rule. Let's do one more. All right. This particular example here, in the previous class, I talked about action selection. I talked about an agent. You have 3 different actions you might want to be able to do, and then you've got some sort of function, based on your current state, you've got some function you're going to compute about which, how good are each of these actions right now. You pick which is the best of those actions. You do that action, repeat. And we sort of base that on the idea of reinforcement learning. And if you want, and a lot of people, when they're doing reinforcement learning, they would start with the situation of, well, maybe I don't know those functions. Everything I talked about in the action selection lecture was more about, was definitely highlighting the fact, well, if you do know those functions, if you know what you want your model to do, so if you have a particular thing that you want your neurons to do, well, just write that down, and those are your functions. But you sometimes might be in a domain where you're like, look, I don't know what my neurons are supposed to do here. I want the neurons to figure it out for themselves. So we're going to try an example of that. We're going to be using the same basal ganglia model and same thalamus model that I talked about last class. So that's what the action selection is going to do. What this particular agent is going to be, though, is a little blue triangle living inside a little environment. I'm slightly showing off here. So Nengo does let you embed just, this is just Python code to generate an environment. Nengo lets you go and connect to any, it's just Python, so you can go and connect to whatever you want. It's got some nice little hooks in it that if your Python code can generate graphics, then it'll display those graphics inside the interface. So that's what I'm using here. But the idea is I'm a little blue triangle, I'm moving around, the black squares, those are walls. My sensors are, I have 5 sort of range sensors sticking out in front of me. Those are these 5 values. That's my state information. Okay. And then what I'm going to do to reward it, so when it chooses an action, it's going to be doing that action. And then what I'm going to do is I'm going to say my error signal for the particular action that I'm choosing right now is the difference between how good I thought it was going to be and my reward signal. And what I'm going to do for a reward signal is it's going to be, if I hit a wall, my reward is 0. If I'm not hitting a wall, my reward is some minimum, say, I don't know, 0.4 plus how fast I'm going. Okay, I just want to encourage it to move forward. If you just do sort of like, okay, you're punished if you hit a wall and you're fine if you don't hit a wall, then these systems just simply learn to stand still or spin around. So we want to give it some encouragement to move forward. Okay. So it initially moves forward, crashes right into that wall, and it's like, oh, that's bad. Life is bad. Ooh. Crashes into a wall, crashes into a wall. Ooh. Okay, hold on a second. I just want to slow down again. I'm just going to go back in time and see what happened there. So it was coming down here. It chose to turn before hitting the wall. Okay, so it's already learned that it should turn in that situation. Okay. And again, all it's doing is applying that same learning rule to those functions that are going between my state information, which is my values of my rangefinders. Okay. And I'm just applying that same learning rule. Oh, there it messed up. It hit the wall, but it's like, okay, fine. It's going to probably just learn to spin. Oh, there we go. It'll spin around for a while. It's around. So, very simple, again, very simple learning rule. For people who are familiar with reinforcement learning, this particular version of the learning rule is not doing the temporal credit assignment part, so it's not looking for, oh, maybe if I do this now, I'll get a reward in the future. Those sorts of things can be added. Again, that's just a different computation of the error signal. And then we just go ahead and apply that to these learning systems. Reset it, try that again. Just reset its brain, let it try again. There it goes. In this particular situation, it starts doing not too bad a job. Okay. Again, I've got the learning rate cranked up pretty high here, which may or may not be a good idea. It's gotten very scared of walls. But there we go. Let's remain to go forward. So, a whole bunch of different ways of doing learning, all of which are actually that same learning rule I just talked about, which is just sort of modifying a decoder, but with very, very different ways of computing the error signal. And what I really like is now, because I've got, again, with this neural engineering framework stuff, not only am I learning in one particular part of the system, but I'm also building the learning process out of biologically plausible components. Okay. So that's kind of fun. Okay, so that was a lot of stuff. I will briefly mention, okay, that's pretty much what I wanted to talk about supervised learning. There's more that could be talked about. There are ways of bringing in things that are kind of like minimal levels of backpropagation, or doing things like maybe we can learn to adjust the encoders. At the moment, we've only been adjusting the decoders in everything that we've been talking about so far. There is more that could be said in those sorts of directions. I've got a paper or two if people are interested. Actually, let me actually point those out. Publications, there we are. So if people are interested in doing something closer to backpropagation and having that adjust the encoders, this paper here, Geometric Interpretation of Feedback Alignment, is talking about if you start doing a biologically plausible version of backprop to adjust the encoders, then you can start talking about, okay, how does that adjust the encoders of a population? And so we can sort of understand that. So if people are wanting to sort of extend things a little bit farther, that would be one place to look. And what else is the other one? Sorry, we need to find that one more. Learn to learn skills. Sorry, I missed. Oh, the neural development model of. Oh, I apologize for not being able to find this. Learning and learns. So this would be, this paper here takes you a little bit more into the STP learning rule, or sorry, this takes a little bit more into trying to connect it into more biologically realistic learning rules, such as the SYDE556 learning rule that's fairly popular. So yeah, so there's a couple other possibilities if people are interested. We've sort of looked at in all sorts of various different ways. Lots of sort of ongoing research to be being done, and I think the core point of it is I like to be able to merge these two things together, or is merge doing some learning in one part of my model, but the rest of my model built with this engineering approach in order to support that learning. There's some more things that we said. You can also, so everything I talked about so far was supervised learning. There's also another big area in neural networks where people talk about unsupervised learning, where it's sort of, okay, maybe I want to learn without an error signal at all. And with rules like the Hebbian learning rule, hey, if one neuron fires and another neuron's firing at the same time, then maybe increase the connection weight between those. There's a couple interesting things. Again, you can actually find that those do an interesting job of maybe doing something like learning what good encoders might be. That's, I think, a much more sort of, there's a lot more things to sort of play with in that sort of domain, so I don't want to focus on it. I don't think there's much more I can focus on it too much, other than to say, hey, yes, all the things that people do with normal neural networks, go ahead and apply it here. I haven't yet found situations where I think there's any particularly new insights that come in from, yeah, that we end up gaining. My hope is what I just showed with the supervised learning is, yes, I do think that the neural engineering framework gives us slightly different ways of thinking about supervised learning. Cool. All right. That's everything that I wanted to say. Thank you very much. And yeah, we will see you next class. Bye.